So do you see lecture 23 at your end?
Yes, ma'am.
Yes. Okay. All right. So I think towards the end of lecture 22, we briefly discussed uniform continuity. So continuing from that point, let's look at one more example. Yeah. Uh, to explain what is the meaning of the statement that a function is or is not uniformly continuous. Yeah. So let's look at something very simplistic. Let's consider the function f defined from the real line to itself. So f is defined by sending x to x square. Okay. So you can use the epsilon delta definition of continuity to show that f is indeed continuous everywhere, yeah, on the real line. Okay. So in particular, no matter what positive epsilon you give me, yeah, uh, yeah. So let's look at, you fix a point x naught in the real line and fix an epsilon positive. Yeah. You look at the point f of x naught and you look at the point x naught, right? So this is in the real line, right? So no matter what epsilon you give me, having fixed the point fx naught, I can look at the epsilon interval around the point f of x naught. So this is an epsilon neighborhood of the point x naught. Corresponding to this epsilon, there would be uh, a delta positive. Now, what does delta achieve for this? For us, a delta makes sure that if I restrict my attention to the delta neighborhood of the point x naught, and if I pick any point in that delta neighborhood, then f must take that point to within this prescribed epsilon neighborhood. Yeah? If that happens for every point of the real line, we would say that the function f is continuous. Right? Now one can check that this can be done for this function. I will leave that for you to check. Right? So I leave that. So I leave that. Yeah, is that okay? Can I leave this bit for you? That corresponding to every epsilon, there is a delta such that this happens. So, upshot of all of this is that f is actually continuous uh, on the entire real line. So once you sort of complete this argument, then this will fall out. Okay. Now, let's look at the following thing. Yeah. Um, what is that I am interested in discussing here? So if this is true for every epsilon positive, in particular, uh, this holds for epsilon equal to 2. Yeah. So let's see. So for epsilon equal to 2, so can somebody help me out if I take epsilon equal to 2 and take x naught as the point 1? What should be my choice for delta? What delta would work? So maybe the question that I'm asking is not very clear. So for epsilon equal to 2 and x naught equal to 1, the statement, which statement that whenever x is in delta neighborhood of x naught, then f of x would be in this neighborhood of fx naught of length 2. Yeah, is true for x naught equal to 1. What should be my delta here? What delta would work for x naught equal to 1 and epsilon equal to 2? It's a very simple function here. F of x is x goes to x square.
Ma'am, it should be 2 upon 1 plus x.
It should be 3 upon 1 plus x.
2 upon 1 plus x, I think. If delta is less than 2 upon 1 plus x, then
see, delta cannot depend on x, right? Delta can possibly depend on x naught. X is something which is varying in this interval, right, Priyanshu?
yes, sir.
Yes? Yeah, so you want to sort of reframe your answer? Give me one delta that will do the job. For example, you know, I think, let's see. So this is x square minus 1 here, right? X square minus 1 in absolute value is less than half. And x minus 1. So I think delta equal to half would do the job. Let's see. So let me make a correction here. So let's see. So if I put half here, is this statement true? I think it is, yeah. Yes, it is, yeah. So x is in this, yeah. So this means that, what does it mean? This means that I am looking at x naught. X naught is 1. And if I take delta to be half, that means that I am looking at the interval 3 by 2 and 1 by 2, right? And f of x naught is again 1, right? And taking epsilon equal to 2 means, yeah, so let's look at 1 plus 2 is 3 and 1 minus 2 is minus of 1. Yes, correct. So if I pick any point x here, then certainly, you know, x square lands in this interval. That's correct. In fact, you know, that's correct. Is that correct? Everybody with me?
Yes, ma'am.
Yes. Yeah. So yeah, so in fact, I would look at x square, right? So x square minus 1 is between minus 1 by 4 and 1 by 4. Yeah, so somewhere here, yeah. This is f of x. Right? So anyways, what is that I want to say? So delta equal to 1 by 2 works for x naught equal to 1. Yeah, conclusion. So I am fixing epsilon equal to 2, x naught equal to 1, and delta equal to 1 by 2 works. Yeah, works in the sense that, you know, this statement that I have written, this one statement, star holds. Okay. All right. So what am I going to do? I'm going to keep epsilon fixed. I'm going to continue to keep epsilon fixed, and let's see. let's see if the statement star that I have written, does it hold true if x0 is 10? Yeah. Consider if statement star is true. Statement star is true for x0 equal to 10. Yeah, so f still continues to be continuous at x0 equal to 10, which means that corresponding to every positive epsilon, there would be a delta, which sort of works. Now, I am asking if corresponding to epsilon equal to 2, does delta equal to 1 by 2 work for x0 equal to 10? Yeah, that's the meaning of saying that statement star is true. Yeah. So let's see. Yeah. So let's look at, so for x0 equal to 10, f of x minus f of x0 is by definition x square minus 10 square, which is 100, right? And what is that we want? So let's look at something here, right? So all I want is that if x is in 1 by half neighborhood of 10, then x square minus 100 should be at most 2 in modulus, right? That's what we want. But let's look at this point. Let me look at, let me see, what should I take? Let me take so something which is in this neighborhood. Let's see if this works. I'm making a guess here. Let's see. So let me take x to be 10 1/4. Yeah. So x minus x0, which is 10, is certainly less than half. Yeah. So then I'm just going to reiterate that for this particular choice of x. But what happens to f of x minus f of x0? This is 10 1/4 square minus 10 square. This is 5 1 by 16, which is certainly bigger than 2. Yeah. So conclusion for epsilon equal to 2, delta equal to 1 by 2 works at x0 equal to 1, but does not work at x0 equal to 10. Yeah. So delta equal to 1 by 2 does not work at x0 equal to 10. Is that okay? Does everybody see what am I trying to say? Is that okay?
Yes, ma'am.
Yes? Okay, excellent. See, although the function is continuous, yeah, which means that delta equal to 1 by 2 does not work, but there is some other delta that will do the job, yeah. Okay. So what is that I want to make? By this example, I want to emphasize the following fact. I want to emphasize that there is, so let me emphasize. So in fact, there is no single delta positive such that the statement, which statement, let me write down the statement star one more time. So this is so I have fixed epsilon equal to 2, and I am saying that let's fix epsilon equal to 2. Yeah, so yeah, I'm looking at the neighborhood of fx0 of length 2. Then there is no single delta such that if I pick points in delta neighborhood of the point x0, then f of x will work in fx0. And I'm not saying that there is no one delta that will work for all the points x0 and R. Right? So sure, I agree with you that there exists a delta. So corresponding to each point x0, there would be a delta such that statement R is true. But what is that I'm saying? There is not one single choice of delta that will work for every choice of x0. You know, the example that we gave upstairs, it seems like delta equal to half works for x naught equal to 1, but delta equal to half does not work for x naught equal to 10. Yeah. So, you know, let me sort of explain why this statement is true. Yeah. Why is that one cannot find a delta positive such that this statement star, so maybe since I already used star for maybe something, so the statement star tilde holds for every point of x0. Yeah? Yeah. So this is essentially saying that this function f fails to be uniformly continuous on the entire real line. However, this function is certainly continuous on the real line. One cannot choose a delta which is independent of the point x0. Yeah. So let me sort of do it step by step. Let me first convince you that why can one not choose a single delta that will work for all points in x0, right? So suppose this is the case. Yeah. So suppose so is everybody with me up till this point? Do you see where are we and what are we trying to do? Suppose there were. Is that okay?
Yes, ma'am.
Yeah. So suppose if not, suppose there were a delta for which this statement star tilde holds for all the points x0 in R, right? Okay. So in particular, this would imply that no matter what point x I pick within the delta neighborhood of the point x0, f of x would lie in this neighborhood of f of x0 of length 2, right? So in particular, let me look at only for positive x0, yeah? So what is it I want to say? So we would then have, in such a scenario, so let me just look at x0 positive and x equal to x0 plus delta by 2. What am I doing here? I am picking, so x is one point, one example of a point which is in, so I have fixed x0. So this is the delta neighborhood of the point x0. We assume that statement star tilde is true, so there is a delta, and I am looking at a point here. Yeah, x0 plus delta plus delta, and just for the sort of sake of convenience, I'm looking at only positive delta for now. Yeah. So let's look at one such point in this delta neighborhood and let's compute. What do I compute? Let's compute f of x minus f of x naught. Yeah. So f, the function f sends x to x square, which means that this is x squared minus x naught square. Now x we have chosen to be x naught plus delta by 2. So this is x minus x naught. So this is delta by 2 times x plus x naught, which means that this is 2x naught plus delta by 2. Right? Is that correct? Yeah, and all of this is positive, so I can just forget about the absolute values here. This is, and just absorb this 2 inside the parenthesis. So what is that I have? So this is exactly delta x naught plus delta by 4. Right. Now I'm working under the assumption that statement star tilde is true, which means that the distance between fx and fx naught is at most 2. Yeah, so this statement holds true for x equal to x naught plus delta by 2. So this is implying, this says that this would in particular imply that so delta x naught is something which is smaller than delta of x naught plus delta by 4. This everything is positive here, so this would imply that delta times x naught is strictly less than 2 for all the points x naught which are positive for some fixed value of delta positive. Can this happen? Can this happen? So hence, for this function corresponding to epsilon equal to 2, there is no delta that will work for all the points x naught simultaneously. Yeah, let me just highlight that. This is what we have shown. Hence, for this function f corresponding to epsilon equal to 2, there is no single delta that will work, meaning the statement star tilde will hold. That will work for all x naught in R simultaneously. Yeah, the same delta works for each x naught as x naught varies through the real line. Nevertheless, the function f is continuous at each point of x naught, at each point of the real line. Yeah. So let me just highlight that. But f is continuous at each x naught in R. But the above discussion shows that f fails to be uniformly continuous on the real line. Yeah, so as I said last time, uniform continuity is a statement about a set. It's a property of a function on a set, whereas continuity can still be defined at a point. Yeah, so let me just recall, in case you've forgotten, recall the definition of uniform continuity. So x and y be metric spaces and f be a function from x into y. Yeah, so let's say, so f be a function between two metric spaces x and y, then this function f is said to be uniformly continuous on x if for every epsilon positive there is a delta positive such that for all the points, let me denote the points in x by x and p, the distance between fx and fp is less than epsilon whenever x and p are within delta distance of each other. Yeah. So the point is that delta is independent of the choice of the points x and p, unlike continuity, where the delta can possibly depend on the point x naught, where the continuity is being considered. Okay, so is this okay? Does this example illustrate the concept of uniform continuity well? Do you follow what I'm trying to say?
Yes, ma'am.
Is that a yes with everybody present here?
Yes, ma'am.
Somebody has a question, please ask. Yeah. So upstairs, we saw an example of a function which is not uniformly continuous. And I think last time also I gave you an example of a function which is not uniformly continuous without proving it in detail. So this time we actually proved that this is not uniformly continuous. And we also saw an example of a uniform continuous function last time. So is this okay with everybody? Okay, all right. Okay. So when, I mean, besides the definition, is there any other way to assert that a function is uniform continuity? Yeah. So the next theorem is the answer to this question and actually plays a very crucial role in theory of integration. But let me state the theorem first. So as you would all guess by now, so in order to say that the function f is uniformly continuous, it better be continuous in the first place. Yeah, for each epsilon positive, if we want one single delta which should do the job for all the points of x, the function better be continuous at least. Yeah, there must be a delta at each point. Whether or not it depends on x is a different question. Next, all right. So let's consider a continuous function and let's see what is the appropriate hypothesis that ensures uniform continuity. Yeah, so it turns out compactness plays a role here. So let me write down the statement of the theorem. So let f from x into y be a continuous function between two matrix spaces x and y. And let's assume that X is compact. Yeah, then it follows that, in fact, F is going to be uniformly continuous on X. So continuous function on a compact metric space turns out to be uniform continuous. Yeah. So one can indeed choose a delta positive to be independent of the point in X. Yeah. So for example, this theorem says that if I look at this function, which we considered upstairs. Yeah. So let me sort of write down that example first. So for example, sorry, let's I'm so sorry. Yeah, so let's look at this function f. Let's define it on closed and bounded interval 0, 1 to r. The very same function, x going to x square, right? Now, we just saw upstairs that this function, it fails to be uniformly continuous on whole of R. But now we are looking at this continuous function only on this closed and bounded interval 0, 1, which is a compact set on the real line. So over here, so let me call it f tilde just to distinguish from that example. F tilde is actually uniformly continuous. On this interval 0, 1. Yes. So again, I would, at the cost of repetition, say that uniform continuity is the property of a function on a set. Yeah. If you extend f tilde to the entire real line, then f tilde fails to be uniformly continuous, as we have seen upstairs. Is that okay? Everybody with me up till this point? Is that a yes with everybody?
Yes, ma'am.
Excellent. Yeah. So let's look at the proof of the theorem. All right. How does compactness of X ensure uniform continuity? Yeah. All right. So let's fix epsilon positive right in the beginning. Okay. Now, given epsilon positive, since the function f is assumed to be continuous throughout the set X, at each point of X, one can get a delta from the definition of continuity that works at X. Yeah, so let me write that down. Since f is continuous on X, by the definition of continuity, for each point P of X, there would be a delta So in order to highlight this dependence of P, I'm saying delta P. So delta may or may not depend on P. If it doesn't depend on P, excellent. The function f is uniform continuous. If it does, then what is that we do is what I'm trying to tell you. Yeah. Such that, so this delta is what we get from definition of continuity, and this works at the point P, which means that this delta is chosen such that so I'm going to write it in a different manner, such that if you pick any point in the delta neighborhood of the point P, let's pick a point X here, then f of X would be in epsilon neighborhood of the point f of P. Yeah, and instead of epsilon, let me just write epsilon. Yeah, so I'm looking at this ball around f of p. This is the epsilon neighborhood of f of p. So this is exactly saying that the image of this delta neighborhood of the point p under f is sitting inside this. Yeah, this is just from the definition of continuity.
Yes, ma'am.
Yes, so Okay, let me be careful and let me just switch to epsilon by 2. Maybe that is better. Doesn't matter. So instead of epsilon, I'm working with epsilon by 2. Nothing changes, right? Continuity says for every positive epsilon, there would be a delta. In particular for epsilon by 2 also, this happens, right? Now, what am I going to do? I am going to look at the balls. So these balls centered at the point P and radius delta P. Yeah. Now allow little p to vary on the set X. Yeah. So for each point P, you get a delta P from the definition of continuity that works at the point P. Yeah. Now, what am I trying to say? So you look at these balls, delta P, right? Now this gives an open cover of the set X. Yeah. So I'm going to say, so note that as I allow P to vary over the set X, then this is an open cover of X. Right? What does it mean? Let's remind ourselves. This means that each such ball is an open set in X, true. And if I take the union over these sets over P in this, then that union would contain the set X, correct? Is that okay? Yeah, and in fact, let me make delta P by 2. Doesn't matter. Some is positive. Is that okay?
Yes, ma'am.
Yes. Now I'm going to appeal to compactness of X and extract a finite subcover. Yeah. So I'm going to.
Ma'am,
Yes, please.
should we take delta P by 2 in the first equation also?
It
If
doesn't
we are
matter.
taking it here.
Doesn't matter. Even if it's not delta P by 2, all I'm trying to say is, so you look at this picture here. All I'm trying to say is that you look at a set X, yeah, and you look at a point P in the set X, and you look at neighborhoods of the point P. Yeah, so this is some positive radius delta P by 2, and allow P to vary throughout X.
Yes, ma'am. Then their finite union will be in this only because of compactness.
Yeah. So whether or not I have in the first statement which comes by continuity, so I guess the first statement you mean this statement 1. Whether I have
Yes, ma'am.
delta P by 2 there doesn't matter. As long as little p is varying throughout the X, the statement is true. I can take whatever I want to. I can take delta P by 3 here, delta P by 4 here, delta P here, anything which I want.
Okay, ma'am.
Correct? Is that okay?
Yes, ma'am.
Yes, you can take 2 delta P, you can take 3 delta P, whatever you want. Yeah. You're not going to miss any point in X because little p is going to vary throughout X. So it will cover each and every point of X. Yeah. Okay. So let's look at the compactness of X and say that since X is compact, there is a finite subcover corresponding to this open cover. So since X is compact, there would be a finite subcover means there exist points P1, P2 up to let's say Pn such that what happens? Such that X is contained in the union of these finitely many balls, right? So I have a ball centered at P1, delta P1 by 2, ball centered at P2. So these are all points in X, yeah. Delta P2 by 2 and the finitely many Pn delta Pn by 2. Is that correct?
Yes, ma'am.
Yes. Now I have these finitely many positive numbers, delta P1 by 2, delta P2 by 2, and so on, right? So let me draw those in this picture. Yeah, so let me make, so this is, let's say, Pn, and this is delta Pn by 2, right? Suppose this is P1, and this is delta P1 by 2, and this is P2, and this is delta P2 by 2, and things like that. Yeah. Now I'm going to look at these finitely many delta P1. Yeah. So I'm going to look at delta P1 by 2, delta P2 by 2, delta Pn by 2. This is a finite set, correct? Each of these is a positive quantity, which means that if I take a minimum, I will still get something positive, correct? Yeah, I'm going to define that minimum as delta. Yeah. So since the minimum here is taken over finitely many positive numbers, thanks to the finite subcover, which in turn owes its existence to the compactness of X, one has that delta is positive. Yeah, so do you realize if there were infinitely many of them? Yeah, so for example, delta pi's can be so let me say delta pk's could be 1 by k, and if I take the infimum over 1 by k, I might get 0 and nothing. And then what do I do? Yeah, so this is very, very important that I have only finitely many, and that's the reason I get delta to be positive. Is that okay? Now I claim that this taking infimum over these finitely many will give me delta, and this is the delta that I have been looking for. Yeah, so what I'm trying to say is that for each positive epsilon, having fixed this epsilon, now this single delta which will work for all the points of X. This is what we have been looking at. So let me just try to convince you that this is the case. So is everybody with me so far?
Yes, ma'am.
Yes. So now I'm trying to convince you that this is indeed the thing that we have been looking for. So let's suppose that I have points in X which are at most delta distance apart. So what is that I have to show? I have to show that Fx and Fp are also at most epsilon distance apart. Yeah, so we will show that. Let me write that. We will show that the distance between f of x, the corresponding images, and f of p is at most epsilon. Yeah. So the same delta would work throughout the set X simultaneously. Yeah, this is saying that F is uniform continuous, which is what that we wanted to do. Okay. So is this okay so far? So let's see how do we do this. Now, yeah. So let's look at the point P. Now the point P is in the set X, and X is contained in the union of these finitely many balls. So P would be contained in at least one of these balls, right? So let me just fix one of them which contains P. Yeah. So choose K. The first thing I'm saying is choose K. So this is from between 1 and capital N, so that the point P belongs to the ball around the point PK. There will always be a K like this. So this is K belonging to 1, 2, up to N. Right? Because this is true because the set X is contained in the union of these finitely many balls. In particular, the union of these finitely many balls contains the point P. Is that okay?
Yes,
Yes,
ma'am.
ma'am.
Yes? Okay, excellent. Now what do I do? Yeah, I have to, the distance between X and the point P is at most delta, and saying that P belongs to this, neighborhood around pk means that the distance between p and pk is at most delta pk by 2. Let me apply the triangle inequality in X, yeah, and try to estimate the distance between X and pk, yeah, this point pk here. So using the triangle inequality gives me that the distance between X and pk is at most the sum of the distance between X and P and pk. Correct? Now, the distance between X and P is delta, and the distance between P and P is at most delta pk by 2. Why? Because P belongs to this neighborhood around pk of size delta pk by 2, right? Now, delta is the minimum of these, delta pi is by 2. So, which means that this inequality is true. Yeah, delta is also going to be less than or at most equal to delta pk by 2, which means that sum this, and this is 2. Yeah, the distance between X and the point pk is at most delta. Yeah, so let me just summarize this. That is, the distance between X and pk is strictly less than delta pk by 2. Is that okay? Yeah, so if I look at this ball of centered at pk and radius delta pk by 2, so this is the radius delta pk by 2. Yeah, so p and x, so let me not draw, let me see. Yeah, sorry, I'll just make a correction here. Instead of delta pk by 2, I will just look at a ball around pk of radius delta pk by delta pk. Yeah, so p belongs to delta pk by 2 neighborhood of pk. So p is a point here. The point P is somewhere here, and our calculation shows that X also belongs to this neighborhood. Yeah, so both the points P and X lie in this ball around the point PK of radius delta PK. Yeah, is that okay? Is that okay?
Yes, ma'am.
Yes. Now let's go back. Let's go up and see. Yeah. Yeah. So let's look at the statement 1. Yeah, what does the statement 1 say? That I have X and so I'm going to replace P here by PK. So you look at this ball of centered at PK and radius delta PK. Then if I pick any point here, then its image is going to land in this ball around FPK of radius epsilon by 2. Yeah. So in our case, it says that Fp and Fx are both going to lie in this ball center Pk radius epsilon by 2. Yeah. So I'm going to apply that here. So I'll just rewrite it in words just to emphasize because you don't see the other screen when I write this. So the above statement says that so that both P and X, the points P and X, lie in the ball centered at PK, radius delta PK. Radius delta pk. Now it follows from statement 1. What was statement 1? Statement 1 was the assertion about continuity of f. Yeah, that is how we got the point delta at each point p. So it follows from statement 1 that both Fp and Fx lie in so let me just write that. What is the immediate consequence of it follows from statement 1 that I'll just sort of rewrite statement 1 here, that statement 1 says I'll say it rather than saying it follows from sorry, I'll say that let's just recall statement 1 here. Recall statement 1 that so this is saying that if you look at so I'm going to apply it to pk, delta pk. Yeah, you pick any point in this ball around pk of radius delta pk, then f is going to map it into, which means that the image is going to be inside this ball centered at fpk epsilon. Yes, is that correct? And in fact, I had an epsilon by 2 there. Yeah, so just recall statement 1 here, so which means that it follows that. Now I'll write that what follows from here is, it follows that since P and X lie in this ball, f of P and f of X will lie in both Fp and Fx lie in, so they both belong to, so I'm going to look at this ball around pk of radius delta pk. Yeah, take its image. Yes. Now fp is a point in this ball around pk, and so is x. So fp and fx both belong to this set, which in turn is sitting inside this ball around fpk of radius epsilon by 2. Is that okay?
Yes, ma'am.
Yes. Okay. Now finally, the one final step is, what is that remains here? See, what is that we are starting out with? We started with any 2 points P and X, which are at most delta distance apart. We have to show that their images, Fx and Fp, are at most epsilon distance apart. Yeah, so this is the final thing that remains. So let's look at the distance. So let's estimate the distance between Fx and Fp now. Finally, the distance in y between Fx and Fp. So again, I'm going to apply the triangle inequality and say that this distance is going to be the less than or equal to the sum of the following two distances: the distance between Fx and Fpk, and the distance between Fpk and Fp. Correct? This is the triangle inequality. However, I have estimated these distances. Yeah. So what can I say about the first thing? How can I estimate the distance between Fx and Fpk? How can I estimate the distance between Fx and Fpk? Let me draw a little picture here, if that makes you feel a little bit better about what is happening. So I have the point Pk, and I am looking at delta pk neighborhood of this point, and then I have the point fpk, and I'm looking at an epsilon by 2 neighborhood of this point. Yeah, so we just showed that X and P are both points in here. Yeah, so X is somewhere here, P is somewhere here. And then we use the continuity of F to show that F of X and F of P are going to
Ma'am,
be,
it will be epsilon by 2.
the first thing will be epsilon by 2, right? So the distance between Fx and Fpk
Yes.
is at most, the first one is epsilon by 2, and the second one is also epsilon by 2. So what does it say? Whenever X and P are at most delta distance apart, then Fx and Fp are going to be at most epsilon distance apart. And this delta is independent of the choice of the points X and P. So hence, this is saying that the function f is uniformly continuous, and we are done. Is that okay with everybody?
Ma'am, I had just one doubt. When
Please
we
go
took
ahead.
delta to be minimum of all those,
Yes,
but if we took it to be maximum, how
yes.
will it violate any
If I take
upcoming condition?
delta to be maximum, then there's no problem. This step will still go through. That delta would still be positive, but look at it where we apply it here. See, at some point, let's look at the second inequality here. See, I use the fact that delta is less than delta p by k by 2 here. See, if you take delta to be the
Okay.
maximum of those, then this inequality will fail, right?
Yes, ma'am. Yes, ma'am.
Yes, it's sort of a chain thing that you're using, right? So instead of looking at, these infinitely many balls which cover X, you just work with finitely many of them. You make sure both X and P, both these points are in one such ball, one such fixed ball, right? So you started with this assumption, right? We started with this assumption that X and P are at most delta distance apart, right? Yes. And then what did we do? With this, we say that we found one such fixed ball around the point pk of radius delta p such that both these points are in this fixed ball.
Yes, ma'am.
That is the crucial step here, right? Yeah. So you did I answer your question? See, this
Yes, ma'am.
inequality
Yes,
is
ma'am.
code, right? Yeah.
Yes, ma'am.
And this is crucial. Yeah. Okay. Excellent. Anything else?
No, ma'am.
Okay. How about others? Is this good with everybody else? Let's see how many audience do I have. I have 13 of you. Yeah. So is this okay?
Yes, ma'am.
All right.
Ma'am,
Excellent. Yeah. Somebody wanted to say something?
ma'am, can you please repeat the last line?
The last line, the triangle inequality part, did you follow that?
Yes, ma'am.
Okay. So now you are saying, why do I have each of these distances to be less than epsilon by 2? Is that what you're confused about?
Yes, ma'am.
Okay. See, let's see. See, we just showed that P and X lie in this ball, the same ball around the point PK, right? And so f of X and f of P, you look at, I'll label this something. You look at inequality 2. F of X and f of P are both points in on the left hand side. Right, so f of X and f of P by the inclusion 2 are in this fixed ball around Fpk of radius epsilon by 2. Is that okay?
Yes, ma'am.
Yeah, so you just look at this picture that I have. So you look at this blue ball, which is a ball in Y centered at Fpk, radius epsilon by 2. F of X and Fp are both here. This is what we have shown. Yeah, which exactly means that the distance between Fx and Fpk is at most epsilon by 2. Correct?
Yes.
Yeah, saying that f of X belongs to this ball around k of radius epsilon by 2 is exactly meaning this, right? And likewise, the distance between Fp and Fpk is also at most epsilon by 2. Correct?
Yes, ma'am.
Yes. So which means that the distance between Fx and Fp is at most epsilon by the triangle inequality. Yeah. So is that Tanmay who asked this question?
Yes, ma'am.
Yeah. So Tanmay, is it okay now? If you are confused, please ask.
No, ma'am, it's okay.
It's okay? All right. How about everybody else? Okay. So shall we move on to the next thing? So this is rather useful, you don't have to look at epsilon and delta, just look at the domain of definition of the function f. If f is continuous and on that domain is a compact set, then we say that the function is in fact uniformly continuous. Okay, so is this okay? Okay, so I believe no answer means yes, unless you stop me. Okay, so the next topic, so this was quite a bit about continuity and compactness. Let's examine the next thing, which is continuity and connectedness. Okay, so here is the statement. So let f be a continuous function between spaces x and y. So let A be a subset of X which is connected. So then the theorem says that its image under F is also connected. So what did it say? A continuous function always takes connected sets onto connected sets. Continuous image of a connected set is connected, just like continuous image of a compact set is compact. Okay. Meanwhile, can you tell me what are all connected subsets of the real line?
All finite subsets.
Okay, all finite subsets are connected. Okay, all right. Let me ask.
Ma'am, no ma'am.
Then what happens?
One second.
Ma'am, all intervals are connected.
Yes. And are there any? Yes. Good.
Means the entire real line is basically connected.
The entire real line is connected. Excellent. And all intervals are connected. Yeah. Whether or not they are open or closed doesn't matter. And these are precisely the only connected sets of the real line. Yeah. So for example, if I have to write down this theorem for the real line, then what would it read like? So I'll just write it like a corollary. Yeah, we'll see the proof of the theorem also. But let me write down a corollary. Maybe you find that interesting. So let f be a continuous function from the real line into itself. Yeah. So unless stated otherwise, real line here has the Euclidean metering. Be a continuous function, right? Now, so let a subset of X be connected. Yeah. So in this case, we will replace phi as we have a characterization of connected sets on the real line, as Kritika reminded us. So let A be an interval in R. Then this theorem says, then its image under F is going to be a connected subset of R. So that means that its image under F is going to be an interval. Yeah. So what did it say? It takes, F takes intervals to intervals. Is that okay? Everybody with me? Is that okay?
Yes, ma'am.
Yes. And moreover, if I have A to be a closed and bounded interval, then what can we say about its image? What more can we say about its image? Under F,
It will be compact.
It will
it
be
will be compact. So it means that it will be closed and bounded interval. Yeah. So let me also write that in the same thread. So in particular, F takes closed bounded intervals to closed bounded intervals. Yes, is that okay? So F takes intervals to intervals. That's because continuous image of a connected set is connected. Now, if I look at further closed and bounded interval, which means that this is a compact set, then it will be a closed and bounded compact set in R. Now, it will be an interval because we started with an interval. Yes, connectedness is also preserved. Is that okay? So I'm combining two things here, that a continuous function takes connected sets to connected sets, and the second thing is a continuous function takes compact sets to compact sets. Is that okay?
Yes, ma'am.
With everybody? Yeah. You know, this corollary, in fact, you know, yields two familiar theorems from first year calculus. One is the extreme value theorem, which I think I already mentioned. And the other is the intermediate value theorem. Yeah, so I'll just write that here. I think it's a good point to remind that. Yeah, so saying that F takes intervals to intervals is exactly saying something which is very, very familiar to you. So this is again a corollary. This is the intermediate value theorem. So what is the statement of this theorem? It says that so let f be a continuous function and what is I? I is an interval in R. Yeah, so f be a continuous function defined on an interval. So let me say f be a continuous function from an interval I. In R, yeah, so let me have 2 points A and B in I, and let's assume that A is strictly less than B. So let's look at the points, their images under F. Those are f of A and f of B. Yeah, so let me draw a picture, something that perhaps you're very, very familiar with, graph. Yeah. So this is the interval I. So suppose that A is here and B is here. A is less than B. Suppose that F looks like this. So this is the point F of A, and this is the point F of B in this picture here, right? Suppose that F of A is less than, strictly less than F of B, yeah, and M be a real number such that M in F of A and F of B. Yeah, so in this picture here, where is M? M is somewhere here. M is somewhere here, right? Then this M is going to be assumed by F, yeah, which means that there is a point C in open interval AB such that M is assumed at the point C by F. Yeah, FC is M. Yeah, so this is saying that so M is corresponds to some point on the picture here. This is C of FC. Yeah, and this is the point AFA, and this is the point BFP. So this is perhaps very familiar to you, the intermediate value theorem. What is that we are trying to say? This is just the corollary of the statement that the continuous function f will take the interval I onto another interval. Yeah, so f of I is an interval. So fa and fb are points in this the image interval, and hence it would assume any point, any intermediary point as well. Is that okay? So does everybody see that the intermediate value theorem is actually a corollary to the theorem? Let me give it a name. Theorem A that I have written here. Theorem A, or corollary 1 and corollary 2. If you want to deduce it from corollary 1, that's also fine. Is that okay? Does everybody see this?
Yes, ma'am.
Yes. Okay. So let's try to establish theorem A. Verify the proof of theorem A. Yeah. Is that okay? Everybody is with me so far?
Yes, ma'am.
Yes. Okay. So what is that we are given? You are given a continuous function between two metric spaces x and y. A subset of x is connected, and you are required to show f of A, its image under F is connected. Yeah? So as we have discussed this before, it is a lot easier to work with something which is not connected. So we will say that suppose FA is disconnected, and let's see what happens. So here I am giving the proof of theorem A. So let, if possible, on the contrary, assume that f of A is disconnected. Okay, so which means that there is a disconnection of f of A, which means that there are, by definition, disjoint non-empty open subsets. Let's call them E and F with, so well, not, sorry, what am I saying? Non-empty separated sets. Non-empty non-empty separated sets. So E and F form a separation of f of A with f of A equals E union F. Yeah. Recall that. What does it means to say? What does it mean to say E and F are separated? Can somebody remind me?
No point of E is a limit point of F and vice versa.
Yeah, thank you so much. Yeah, no point of E is a limit point of F, and no point of F is a limit point of E, which means analytically the following. Yeah, thank you so much. Okay. So I'm going to make a simplification of notation, and I'm going to write let me write yeah, maybe this helps. Write f of A as S. Yeah. So I will just replace f of A by S everywhere. Let's see if that helps. So S, yeah. Okay. So the first claim that I am going to make is that both E and F are in fact open in S. So we will show that E and F are open in S. Yeah. So let's see. Yeah. So for this, let's look at the following thing. Yeah. Now, let me look at this. Yeah. So since so let's see how do we show this, and why do I need this? Let me just go through this, and then maybe I will try to explain as to what am I trying to do. So the way I'm going to show is that let's look at E. Yeah? You know, the set E is, you know, S is the disjoint union of E and F, which means that E is the set S set minus F, and F is the set S set minus E. Yeah. So in order to show that E and F are open in S, it suffices to show that you know, E would be open in F if and only if F is closed in S, right? So I will note this. It suffices to show that. So let me say. To verify that E is open in S, it suffices to show that F is closed in S. Yeah. Let me, so hence E is open in S if and only if its complement, which means the set F, is closed in S. Is that correct? So instead of showing, and likewise a similar statement is true for F. Yeah? F is open in S if its complement, which means the set E, is closed in S. Right? Is that okay? So in order to show that E is open in S, I would like to show that F is closed in S. All right? Everybody with me?
Yes, ma'am.
Yes? Okay. Let's see how do we show that F is closed in S. Yeah. Yeah. Also recall. Now recall that by definition E and F are separated, which means that no point of E is a limit point of F, yeah, which means that E does not intersect the closure of F. So this exactly means that the closure of F is contained in the complement of the set E. Correct?
Yes, ma'am.
Yes, but the complement of the set E is exactly the set F. Now this is equal to the set F because S is E union F. Now what does it say? It says that the closure of F is contained in F, and F is always contained in the closure of F. What does it mean? So this says that F contains all of its limit points. And hence F is closed in S, which would imply that E is open in S. Is this okay?
Yes, ma'am.
Yeah, is this okay with everybody present here? So similarly, you know, one can show that the set F is also open in S. I will leave that for you. Yeah, so similarly, one can show that F is open in S, yeah, by showing that its complement is closed in S. Yeah, I'll leave that. It's a similar argument. Okay, having shown that E and F are both open in S, what do? We use the fact that, see, ultimately, what are we trying to do? Now, this set S, we started with S. So let's remind ourselves what is that we are trying to do. Yeah. So I have x here, y here, f, which is a continuous function. A is a subset of X. I am looking at its image f of A, which is set S. I am looking at a separation of S. Now A is given to be connected. I start with a disconnection. I start with a separation of f of A, and I am going to use that information to somehow construct a separation of the set A, which will be a contradiction because A is connected by assumption. Is that okay? So what am I trying to do? I said that let's consider a separation of f of A, which is, right, S as disjoint union of two non-empty separated sets E and F. And now let's pull it back by F. Yeah. So now let's look at the sets F inverse E and F inverse F. Yeah. Now since E and F are open in S and F is continuous, sets are open. Is that okay? Since
Yes, ma'am.
E and F are open in S and F is continuous, the pullbacks are also going to be open sets. Yeah. So can I take 4 more minutes and finish this result? Is that okay? Are you all available?
Yes, ma'am.
Yeah. Thank you so much. Okay. So I have two open sets here, right? Now, here's the first observation. The first observation is that these two sets are disjoint. Why? Because the sets E and F are disjoint, right? If this intersection of the pullback of the set E and F under F, the map F, is non-empty, that would imply that E and F are have something in common, which will contradict the fact that E and F are disjoint. Is that okay?
Yes, ma'am.
Yes. And the second statement is that the set A that we started off with is actually the union of these two sets. Again, this follows from the fact that f of A is the union of E and F. You start with the point in A, its image belongs to the set S. So the image is either in the set E or in the set F, which means that if you pull them back, then that is going to be in the set either F inverse E or F inverse F, right? So you see, where am I heading? I am using these steps to construct of the set E. So I am going to say that F inverse E and F inverse F are two non-empty sets which form a separation of the set E, which means that F inverse E, F inverse F, these are two separated sets. Yeah. So how do I show that? I show that F inverse E and F inverse F are both closed in A. That's the next statement. How do I get this? I get it because recall that the pullback of the set E under F is exactly the set A set minus the pullback of the set A. Yeah, so I'm using, so this is statement 1, statement 2. So I'm using this statement 2 here. Actually, both statement 1 and 2. saying that A is the disjoint union of these two sets is exactly saying that the pullback of the set E under F is the set A minus the pullback of the set F under the map F. Yeah. So already we know that this set is open in A, so its complement is going to be a closed set. And similarly, likewise, the other statement. Yeah. Now, if they are closed sets, which means that they contain all of its limit points, which means that the next statement would be, so this is statement 3, and this is statement 4. That the closure of the set in A exactly equals the set itself because it contains all of its limit points. And the similar statement is true for the set F also. And hence, combining the above observations, it follows that these are indeed separated sets. So we have been able to construct a separation of the set A. This contradicts the fact that A is connected, and we are done. I think I overshot by 8 minutes or so. Yeah, this is not done, but thank you so much for your cooperation.